This is a continuation of our discussion of intermolecular forces. And here we're going to talk about phase changes. Now, in Chem 1, we talked about the three states of matter: solid, liquid, and gas. The solid being the most condensed, where the atoms are fixed into place. Liquid being mobile, and a gas, all the atoms are separated. So condensation is the process of changing a gas into a liquid, and vaporization is the process of changing a liquid into a gas, right? So these two processes are opposite one another. Condensation, gas to liquid; vaporization, liquid to gas. Okay? So the heat of vaporization is the enthalpy change that occurs when 1 mole of a liquid substance is vaporized. So in other words, you're going from 1 mole of the liquid to 1 mole of the gas. Okay, so he said these two processes are opposites. Okay, so vaporization and condensation occur at the same temperature, but the magnitude of the energy change is the same, but the sign is reversed. Let's talk about the temperature first. Okay, so we know that water boils at 100 Celsius, correct? You heat a sample of water, you heat it to 100 Celsius. What happens at 100 Celsius? It starts boiling. At the same time, if you have a sample of gaseous water and you begin to cool off that gaseous water, at what temperature does it begin to condense to a liquid? 100 Celsius. So these two processes occur they're opposites, but they occur at the same temperature. Now, the magnitude of the energy change is the same, but the sign is reversed, right? So H2O liquid to H2O gas, that's vaporization. Okay, that is for water, that's 40.7 kilojoules per mole. And H2O gas to liquid, that's condensation. That's negative 40.7 kilojoules per mole. So the magnitude of the energy change is the same, but the sign is reversed, right? So notice that vaporization is endothermic and condensation is exothermic, right? For measuring enthalpy changes, a negative sign is always exothermic. Exothermic means energy out. And endothermic means energy in. Okay, energy out and energy in. So the vaporization is an endothermic process. That's a positive number, that's endothermic. It takes energy to vaporize a liquid, right? Because you're having to tear apart those intermolecular forces of attraction. We talked about how water is hydrogen bonded. Okay, and you've got to overcome that hydrogen bonding when you vaporize water. Okay, now freezing and melting are also opposite processes. Freezing is the changing of a liquid into a solid, and melting is the changing of a solid into a liquid. But again, these two processes occur at the same time and the same temperature. Okay, so we define the heat of fusion as the enthalpy change that occurs when 1 mole of a substance melts. So that's basically defined for the melting process, solid to liquid. So again, like I said, these occur at the same temperature, but the magnitude occur at the same temperature, and the magnitude of the energy change is the same, but the sign is reversed. So again, let's talk about the same temperature. Both these processes occur at the same temperature. So if you have solid water, let's say ice, and you start You start increasing the temperature. When does the ice start to melt? At 0 Celsius. You have liquid water and you cool it until it starts to freeze, starts to convert to a solid. When does that happen? 0 Celsius. The two processes occur at the same temperature. Okay, so the magnitude is the same, but the sign is different, right? So this first process is solid to liquid. That's melting. And the second process, liquid to solid, that's freezing. Okay, so melting is an endothermic process, right? That sign is positive, and freezing is an exothermic process. That sign is negative. So, all right. So let's go. Last is sublimation and deposition. Sublimation is the changing of a solid directly to a gas. And deposition is the opposite of that. It's changing of a gas directly to a solid. These occur without going through a liquid state. Right, so that's all I'm going to say about those. So let's talk about heating and cooling curves. So this shows the changes that occur when heat is added or removed at a constant rate from a particular sample. Okay, so let's say we want to generate a cooling curve for the cooling of 2.5 moles of water vapor initially at a temperature of 130 Celsius. All right, so we're going to do a cooling curve. We're going to start with water vapor, right? We're at 130 Celsius. We're over the boiling point of water, so we're dealing with water vapor. So we're going to cool that water vapor. What you're going to get is you're going to get a graph that looks something like this. Okay, so we're starting with a gas. We're starting with water vapor at 130 Celsius, and we are going to cool off. We're going to cool off that water vapor. And so we're going to see a steady drop in temperature, right? We have heat removed on this axis and temperature on this axis. So we're going to remove heat, and the temperature of the gas is going to drop off until we reach 100 Celsius. Okay? What's special about 100 Celsius, right? That's the boiling point of water. It's the temperature where water boils, but it's also the temperature where gaseous water will begin to condense to a liquid. So here we begin to condense the gas to a liquid. Okay. Now what happens is the temperature stays constant during that phase change. It doesn't matter whether you're going heating curve or cooling curve. The temperature stays constant during the phase change. So the temperature that's coming out is coming from that phase change. Okay, and the temperature stays constant during the phase change. So this temperature stays constant until all the gas has been converted into a liquid. Now we have only liquid. Now the temperature can start to cool off again, right? We're still removing heat. Further we go along here, we're removing heat. So our liquid is cooling off, and then we get to 0 Celsius. What happens at 0 Celsius? It starts to freeze. So we start going to liquid to solid. So again, we have a point here where the temperature remains constant. Heat's still coming out, but the temperature remains constant. The heat's coming out of the phase change. Okay. Now, once all the liquid has converted into a solid, we have no more liquid. We only have solid. Notice we only have a block of ice at this point. Then the temperature starts to drop again. Okay. And then there's no more phase changes after that. So what we want to do is go in and calculate the energy change for each one of these processes at each one of these points along the graph. Okay. So the first point is we're cooling. All we're doing in the first part is we're cooling water vapor, right? So we're going from water vapor, 2.5 moles was specified in the problem, 2.5 moles of water vapor at 130 Celsius to 2.5 moles of water vapor at 100 Celsius. So as the heat's removed, there's a corresponding change in the temperature of the water, like I say, from 130 down to 100. So basically this is basically a heat capacity problem, which is something you should have covered in Chem 1. There's no phase change here. All we're doing is cooling gaseous water. Okay? So it's just a heat capacity problem. Q is mc delta T, where m is the mass or the number of moles. It depends upon your unit that C is in. C is the specific heat of water vapor, which is 33.1 joules per mole per Celsius. And like I say, m is mass or number of moles. So we're going to take 2.5 moles. That was specified in the problem, times 33.1 joules per mole per Celsius, right? So your moles will cancel, and that's going to give us, and your Celsius will cancel ultimately, and that's going to give us units of joules. But why did I say 100 minus 130 and not the other way around? Okay, anytime that you get entered, anytime you do a change in number of moles of gas, change in temperature, any kind of change is always final minus initial. So our temperature change is defined as the final temperature minus the initial temperature. Okay, it's always final minus initial. That's why we're doing 100 minus 130. 130 was the initial, 100 is the final, so this comes out to be a negative number, right? So it comes out to be negative 2482 joules or negative 2.482 kilojoules. Negative sign means it's exothermic, right? We're getting energy out. This is a cooling process. So we get energy out, cooling, energy is coming out in a cooling process. Okay, so we've cooled our water vapor from 130 down to 100. What happens next? What happens next is once we reach 100 Celsius, the condensation begins. Okay, so we get gas condensing down to a liquid, and like I said, the temperature remains constant as the phase change takes place. We're going from gas to liquid, right? So going from 2.5 moles of gaseous water to 2.5 moles of liquid water, right? So our heat change, or enthalpy change rather, is the number of moles times the negative of the heat of vaporization, right? Why the negative sign, right? Because we're doing the reverse process. Vaporization is liquid to gas. We're going gas to liquid. And remember, the magnitude of the energy change is the same, but the sign changes. Okay? So we're doing the reverse process. We're doing the reverse of vaporization. That's where the negative comes from. So we go, heat flow is 2.5 moles times negative 40.7 kilojoules per mole is negative 102 joules. Note that's quite a bit more energy that we got out than in the last process, right? Remember I talked about how vaporization requires energy. It requires a fairly substantial amount of energy, 40.7 kilojoules per mole, to tear apart that hydrogen bonding, to rip those water molecules apart from one another. And when that gaseous water condenses back down to a liquid, that's energy that we're getting out now. That basically 102 kilojoules. Okay? So, now all the water vapor is condensed to a liquid. Now we have liquid water. Okay, so now what happens? If the phase change is complete, the water starts to cool down again. Okay, so heat is removed. So now we're back to a heat capacity problem. There's no phase change here. We're going from liquid water at 100 Celsius down to liquid water at 0 Celsius. Okay, so we're going to use a heat capacity problem. Specific heat is the heat of liquid water, which is 75.4 joules per mole per Celsius. Now, if you're curious, if you want to know where that number came from, I've always remembered the heat capacity of water is 4.184 joules per gram per Celsius. This is per gram, and this number is per mole. Just 4.184 times 18, which is the molar mass of water. That's how you get the 75.4. Now, our temperature change, okay, again, always final minus initial, right? So our final was 0, our initial was 100, so our temperature change is minus 100. So we're going to say 2.5 moles times the temperature change of minus 100 times the heat capacity, or I'm sorry, the specific heat capacity of water, that's negative 18.8 kilojoules. Not a tremendous amount of energy compared to what we got out from the condensation. Okay, so now what do we got? At the end, now what do we got? What do we got now? We've got liquid water at 0 Celsius. So what's going to happen next? The water is going to start to freeze. Okay, so the water begins to freeze, and the temperature, again, the temperature is going to remain constant as the phase change is taking place. Right, so we're going to go from we're going from liquid water to solid water. All right, so our energy change for this process is going to be the negative of the heat of fusion, because we're doing the reverse process of fusion. Fusion is defined as solid to liquid. We're going liquid to solid, right? So our enthalpy change is the number of moles, the negative of the number of moles times the heat of fusion. Okay, heat of fusion of water is 6.02 kilojoules per mole. All right, so our enthalpy change is going to be 2.5 moles times the negative of the heat of fusion times, and that's it, and that comes out to be minus 15 kilojoules. Again, not a tremendous amount of energy that we got out. Okay, so now what do we have? Water is frozen. There's no more phase changes. We now have water. The temperature is just going to drop steadily further as heat is removed. So if we wanted to calculate any energy change from this point forward, it's simply going to be a heat capacity problem. Q equals mc delta T, where C is going to be the specific heat of ice, 37.6 joules per mole per Celsius. Each of the phases of water has a different specific heat capacity. So you can't use that of liquid water or that of steam either. So let's say that we want to cool it to minus 40 Celsius. So our temperature change will be, again, final minus initial. So minus 40 minus 0 is minus 40 Celsius. So we're going to say 2.5 moles times 37.6 joules per mole Celsius times minus 40 comes out to be minus 3760, or minus 3.76 kilojoules. So what we did was we calculated the energy change for each one of those steps along that cooling curve. And that wraps it up for phase changes.